welcome back. In this video, we'll talk about the chi-square test for independence, which is a technique we can use to compare two categorical variables. So let's get started. So we'll begin by outlining the chi-square test for independence, what the chi-square test statistic looks like, what we can do to work with it, and then we'll see some examples. So the use of screening mammograms for breast cancer has been relatively controversial for decades because there may not be the benefit that one would hope to see. So several large randomized studies have been conducted in an attempt to estimate the effect of mammogram screening. So we're looking at data from a 30-year study to investigate, well, how effective are these at really reducing the mortality rate from breast cancer? So we've got a large data set coming to us from Canada with over 89,000 female participants. During a 5-year screening, each woman was randomly assigned to receive either annual mammograms or the standard physical exam for breast cancer. During the follow-up periods, each woman was also screened for breast cancer using the standard of care at her health clinic. So what we're looking for here is there evidence that the mammograms for the enhanced screening are associated with a better outcome. So in order to compare these two categorical variables, we have breast cancer mortality, which is a survived or not survived type variable. We also have a type of treatment, either mammogram screening or standard breast exam. So we'll need to use a chi-square test for independence here. So the null hypothesis here is essentially that the row variable is independent of the column variable. So think about describing this data in a two-way contingency table. Are the variables related? The alternative hypothesis is then that there is, in fact, an association or a relationship between the two variables in our data. Now here's the test statistic that we'll use to help us evaluate this test. It's referred to as a chi-square test statistic. The basic idea is that we'll take the number of categories K. So for each category, we'll calculate an expected count, so what we would expect to get if there was no relationship or no association between the variables. We will calculate the difference between the observed and expected counts, square it, divide by the expected counts, and then add those all up. So if there's not much difference between what we observe in our data, those O's, and what we would expect if the null hypothesis were true, those are the E's, then we should get a relatively small chi-square test statistic. If we are seeing large values, that means that there are bigger differences between the observed versus expected counts. Now we refer to this as the chi-square test statistic because it follows a chi-square probability distribution. This chi-square distribution is defined on positive values only, which makes sense because we're squaring that difference between the observed and the expected, so that can't possibly be negative. This is also a right-skewed probability distribution, so that means it has a heavy tail to the right of the distribution. Finally, the higher the number of categories, the higher the expected value of the test statistic because we're adding more terms to calculate this chi-square. So the values of the chi-square test statistic that should be deemed unusual, well, that depends on how many categories we have in our data. So there's no rough rule of thumb here. Here you can see a couple examples of how the chi-square distribution is actually changing as K changes. So the smallest number of categories that we could observe is 2. Looking at this, we would highly expect, or most of the time, we would expect to see chi-square test statistics in the 0 to maybe 5 range. As we increase the number of categories K, we're increasing the values, or we're shifting that chi-square distribution up toward the right. So again, the higher the value of K, the higher the number of categories, the higher chi-square we would expect to see if there was no association. Now there's one parameter here that helps us describe the chi-square distribution, and that's the degrees of freedom. Here that is the number of categories K minus 1. So that tells us what values we should expect to see. Now, in a chi-square test statistic, or in a chi-square test, what's going to be more unusual? Well, the farther our observed and expected values are away from each other, the bigger that chi-square test statistic is going to be. So values that suggest that, hey, there's no relationship between these variables are going to be in this greater than region. Now, in a test for independence, our categories are the combinations of two categorical variables. So here we actually have two indices or two subscripts. We have our row variable, which has levels going from 1 to all the way up to the number of rows in our contingency table, so we'll call that R. Our number of columns, we have 1, 2, all the way up to C. So here, the same test statistic, just denoted with two subscripts, one indicating the row, one indicating the column. Now, there are some basic rules of thumb that we need to satisfy here in order to do this chi-square test. All of these kind of boil down to the sample size. Is our sample size large enough for this to be a good method? Some recommendations here are that none of the categories should have an expected count or an expected frequency less than 1. So we won't get too deep into the details of how to calculate these, but none of these expected e's should be less than 1. Another restriction that we often place is that no more than 20% of the categories should have expected frequency less than 5. All of this kind of comes together to say that our sample size really just needs to be large enough. I mentioned these two categories or these two conditions in particular because if they're not satisfied, R will throw you a warning. So if you see a warning in your chi-square test statistic output, it's probably due to one of these rules of thumb being violated. Again, we're really just trying to make sure we have a big enough sample here. Now, luckily, we have over 80,000 women in this breast cancer study. Certainly that is a large enough sample. So is there evidence that screening method is associated with outcome? Let's look at the table first. So we have our mammogram group and our control group. In that group of women who were receiving annual mammograms, 500 died from breast cancer, over 44,000 did not. In the control group, 505 died from breast cancer, over 44,000 did not. So this table tells me two things. Overall, the rate of death from breast cancer is relatively low, and there doesn't appear to be much of a difference between the mammogram group and the control group. But this could just be due to random chance, so let's do a formal test. Our null hypothesis here is that there's no association between the screening method and the outcome, whereas our alternative hypothesis is that there is an association. So this is very similar to ANOVA, whereas there is a difference in the alternative or there is not a difference in the null. We're looking at sort of a binary set of hypotheses. Now, if there's no association, then the proportions in each group should be approximately equal. We should see about the same proportion who survived and died. Now, unfortunately, when we have a very different size in each of the groups, that becomes difficult to see. So when we look at, say, a bar chart, the number of people who survived is so much greater in magnitude than the number of people who died from breast cancer that we really can't see whether or not there's much of a difference between the group memberships. So one tool or one change that we can make in our code is to add this scale argument. So here I'm changing the scale on my y variable. My y variable is also continuous, so that's what this continuous part of the function is indicating. And I'm changing it to be scaled based on the percent. So now this y-axis represents the percent in each in each group within a particular subcategory. So here we're seeing that in the group of women who died, about 50% were in the mammogram group, about 50% were in the control group. Out of the women who survived, about 50% were in the mammogram group, about 50% were in the control group. Now, in order to do this chi-square test, we first need to create a contingency table. So I'll create a two-way table in R using that tally function from the Mosaic library. So I'll tally up group based on outcome from this screening data. And then once I have that table created, I'll simply pass that into the chi-square.test function. So doing a chi-square test on my table, I get a very small value of my chi-square test statistic. That indicates that the observed and expected counts were really, really close. My p-value is very high, so there's not much of a difference here between the control group and the mammogram group. So based on our sample, we would fail to reject this null hypothesis. There's really no evidence to suggest that the screening method and the outcome are associated. Now let's take a look at another example. So malaria kills more than 1 million people worldwide and is spread by a mosquito. So this is caused by a virus that spreads between hosts by infected mosquitoes. So if a mosquito bites someone with malaria, picks up the virus, and goes and bites someone else to spread it. The more people that are bitten by each infected mosquito, the higher the transmission rates. So we might be interested in how mosquitoes behave once they have picked up this malaria. So researchers captured 262 mosquitoes that had human blood in their system and measured two attributes: whether the mosquito was infected with malaria and whether or not they had recently fed on the blood of more than one human. So they used DNA fingerprinting to try to identify whether or not there was only one person's blood present in the mosquito or multiple, indicating that they had recently bitten multiple people. Of the 173 uninfected mosquitoes, 16 had recently bitten multiple people. Of the 89 infected mosquitoes, 20 had bit multiple people. So is there an association between whether or not a mosquito is infected with malaria and how many people it's biting? So our null hypothesis is that there is no association between the Plasmodium infection, which causes malaria, and the number of people a mosquito bites. Alternative hypothesis, there is an association, there is a relationship. So here is our data, again reproduced in this two-way table. Now, looking at this proportional bar chart, so that's a phrase or that's a term we can use to describe these bar charts that are scaled based on percents. Here's what we're seeing. Overall, most mosquitoes only had one person's blood in their system. That's indicated by the blue being the most common in both groups. Of the infected mosquitoes, though, they look more likely to have bitten multiple people. This multiple people bar is a little bit bigger, quite a bit bigger in fact, almost twice the size, in the yes group, so the mosquitoes that were infected with the Plasmodium compared to those who were not. So again, we'll create that two-way table using the tally function. We will use chi-square test on that table, and we get a p-value that is very, very small, 0.006. So here, based on this sample, we can in fact reject the null hypothesis. There's strong evidence to show an association between whether a mosquito is infected with Plasmodium and how many people it bites. In the next video, we'll take a look at a slightly different variant on the chi-square test, the chi-square test for association. I'll see you then.